Ladies and gentlemen, hailing from the JOANNEUM University of Applied Sciences in Graz, Austria, we'd like to welcome you to the presentation of our contribution to the AIAA Design, Build and Fly Contest of 2021. We are the JOANNEUM Aeronautics DBF team, and this is Stingray, a fixed-wing electronically powered UAV capable of deploying and retracting a sensor element mid-flight. We start with the overall dimensions of the aircraft. The most important design driver was the limitation of the wingspan to a maximum of 5 feet or 60 inches. In accordance with this requirement, the final Stingray model measures a wingspan of approximately 59 inches. The total height of the UAV amounts to 20.2 inches, combining a 10-inch vertical stabilizer, a 5.7-inch fuselage, as well as a 4.5-inch landing gear. In order to provide enough space for internal electronics and payload itself, the fuselage measures 64.6 inches in length and 5.1 inches in width. Before designing the actual aircraft, trade and sensitivity studies were conducted in order to determine the UAV solution that would generate the highest score according to the original mission requirements. By analyzing the applicable scoring requirements as well as the physical limitations, the trade study provided insight into the preliminary design and laid out the groundwork. The results, in a nutshell, lead to the conclusion to focus the design on a large and heavy sensor and exceeding in the according mission profile rather than developing a small sensor and opt for a greater number of containers. Next, let us examine the weight of each configuration and the differences between missions. Mission 1 is a staging flight which shall prove that the UAV is capable of completing the course as intended. The configuration for this mission only consists of the UAV itself and does not need to include payload. The gross weight for Mission 1 amounts to 9 pounds. Mission 2, the delivery flight, requires the UAV in full gear, payload plus deploy and recovery mechanism. With 4 additional containers, the weight of this configuration is about 14.4 pounds. Lastly, in Mission 3, the UAV must perform its main purpose, the deploying and recovery of a sensor element. With no additional payload needed for this mission, the gross weight of the aircraft amounts to 10.6 pounds. The propulsion system of Stingray consists of 3 main components. For the thrust generation itself, you utilize the Scorpion S2 motor, which is connected to an electronic speed controller and supplied by a 200 watt-hour lithium polymer battery offering 3000 mAh. The motor also drives APC propellers in 3 different sizes depending on the mission profile. Integrated into the aircraft, the combination of these components allows Stingray to go this fast, which is approximately 85 miles per hour. Based on the preliminary design as well as on the trade study, first performance estimations could be made which were consecutively analyzed in the following test flight. The estimation for the general system performance proved to be rather accurate, even outperforming previous anticipations, as can be seen in the number of completed laps for Mission 3 or the overall top speed of the aircraft. On the other hand, the sensor element and its tow cable became subject to a few redesigns in order to improve its stability. The control architecture of the aircraft consists of several different servo motors responsible for actuating the nose wheel, the mission-specific gear as well as aerodynamic control surfaces. Each wing as well as the empennage, which in our case consists of a single elevator, incorporates such steering elements in order to deflect the respective control surface. The same goes for the nose wheel in the front. Driven by a separate servo motor, it ensures a better directional control on the ground. The deploy and recovery mechanism utilizes a microcontroller with an Arduino IDE Plus motor and electronic speed controller to operate the winch, effectively lowering and retracting the sensor element. This sensor element is equipped with a battery powering the 3-bar lights with 2 times 12 watts emitting red, white and green light. That's enough theoretical data for now. Let's start into the demonstration portion of this presentation. Before we take into the air, A technical inspection shall check the functionality of all implemented systems and the aircraft itself. At this point, an investigation from all viewing angles is a must. After examining the basic functionality, the next step is to have a look at the mission equipment. This encompasses the sensor deploy and recovery mechanism, as well as the sensor and its lights. Please note that in this video the nylon string which is tied to the sensor stabilizer is just a measure to keep the sensor straight for filming purposes. Moving on from the technical inspection, let's have a look at Stingray in action. More specifically, we start with a takeoff demonstration. Each flight inevitably comes to an end, and to prove that Stingray can handle the stage of flight as well, here's footage of a few landing approaches. Finally, let's have a look at the main mission profile of the competition, deploying and recovering a sensor element during the flight. The deployment process works as follows. First, we open the hatch and start to deploy the sensor via remote control. At the predefined tow cable extension at about 40 feet, the winch stops. The sensor is now fully deployed, stable regarding its attitude and ready for operation. So we fire the lights. Side note, the sensor itself measures about 24 inches in total length and about 18.5 without the stabilizer. After completing the laps and observing the performance of the aircraft, the sensor needs to be recovered again. Similar to the deploying process, the commands are given by an operator from the ground. Finally, the sensor is secured and ready for redeployment. Lastly, we'd like to thank our sponsors, Montana Aerospace, AC Stereo Mobilitätscluster, Amelia International, Celerion, Noos Gorbruck, Federnerzeugung Sampel, Föstalpine Böhler Aerospace, and of course JOANNEUM, University of Applied Sciences.